What we're demoing is NX CMM, which is part of NX, an application within NX that allows me to inspect fully qualified a model in NX, like what I have right here. This is a part that's in NX. It's a native NX file at this point, and what I want to do is I want to take it into the NX CMM process. So what I do is I'll go ahead and tell it that I want to create a new, and just like as if I was creating a model or a drawing or going into CAM, I can create what we call a standard inspection, which will allow me to bring a machine, a probe, and a head in, a setup. Or since most of the CMMs are, you don't usually change machines and heads in here, we also have what we call templates. And the templates will allow me to bring in different machines, configurations. For example, if I want to bring in a Sheffield, and what it'll do is it'll take this part, place it on a Sheffield machine, and in that machine is going to have a probe changer and a number of probes that are already in place. So it saves me the trouble of having to repeat bringing in something from the same type of a machine. It does it in an assembly context, so and it builds the assembly, as you can see here, which is you can also add individual components to it to make it as realistically similar to the process that you have in the CMM inspection room or on the floor. I can come in, for example, and tell it that I want to add, let's say I want to bring a fixture in. So I can say I want to come down here and bring a fixture that the part's sitting in. I'll just place it around 0, 0. And now I have something that I can also check for collision checking to make sure that aside from the collisions between the probe and the part, I can also look for additional parts on here. For example, like fixtures or calibration artifacts or something like that on here. Okay. Now the model itself, if I go back and look at the model back in the NX environment, the model itself has something inside we call PMI, which is Product Manufacturing Information. This PMI is embedded into the model, and I'll give you a couple of examples here. It's a view dependent. It doesn't have to be in the view itself, but it makes it easier to interpret the different features that are here. So you can see I have some size tolerances, I have positional tolerances, I have datums defined. If I look to another view, you can see where I have more. I have some direct tolerances or lengths on here, and again some more datums, and then some geometric tolerances on here. This type of data is going to be used to flow this information directly into NX CMM and allow me to define the features, the tolerances, and the paths if I desire, without having to error repeating reading dimensions and stuff off of a drawing. So if I go back to my setup that I had here, and I look at the CMM inspection, expanding the navigator, you can see that there's a lot of folders in here, placeholders if you will, but they're pretty much empty. So what I can do is I can come down here and I can say I want to go ahead and I want to link to the PMI. So that data that you just saw, the PMI data that's in here, I can say I want to bring it into the model. So when I pull the trigger on this and say yes, if you look at the navigator here in a second, you're going to see it populated with a lot of information, as well as a report coming up of what data was brought in, and if there was any issues where the PMI did not come through, it would also be in this report. So I can tell it that what I want to do is I'm going to go ahead and generate it to bring everything up to pass, up to date. And then I have a couple of options here. I can go in and one of the things I'm going to do is I'm going to go in and classify that part as a part. So I come over here, I'm just going to select it, and it's classified as a part. So what I'm going to do now is I can go in and do some collision checking on it. So I want to simulate the process, and in the simulation I want to go ahead and turn collision checking on, and I want to define the pairs that I want to use for collision checking. So I can say, rather than having to select components, since they were classified in there, I can say I want you to check everything that's classified as a part, and the part lights up, and I want you to check against anything that's classified as a tool. So you see all these tools will light up briefly. Okay? So it's saying that I don't have to go in and pick each tool in a part. So anytime I use any of those tools, it will be checking for collision between those in the part. So if I go ahead and turn the simulation on, you can see that it's actually, let me move this out of the way, make it a little bit easier to see. You can see that it's actually simulating the machine, same as it would on the floor. It's going to go over there, it's going to pick up the tool. If you have a tool rack, it'll put it in there. And then it's going to go through the process, and it's going to be looking for any collisions that may occur. It'll check for shanking, so it's not just collision to collision. It'll look at the tool configuration and check to see if it's going to shank. Or in the case that's coming up, I'm pretty sure, it's going to measure that other face, so it's going to start going through the part, and it's going to stop, and it's going to light it up and tell me that I have a collision. Okay. So I can either continue and run through the whole process, or I can stop it right there. So now if I look at the paths that I have, you can see that, excuse me, you can see that I have a little difference here. I've got a motion to the clearance plane for that first datum. I've got motion to the clearance plane when it goes over there. When it goes to that pump face, it's going to move up to that position and then move over to here. So that collision is no longer going to be in effect. But the interesting thing is that if I look at here, the configuration of that probe lends itself to shanking on either the sensor or the probe configuration somewhere itself. So you can see that each one of those points, it'll go to a measurement point, it'll go to the next measurement point, and then it can't reach the third one because of the configuration. It'll shank there, so it's going to back out, move up, it's going to change angles, and then it'll move down and measure it. So this is probably not the most practical way because each one of those angles would have to be calibrated, but it is showing you that the software is clever enough to get in there and manipulate it to a point of where I can get to the part. Realistically, you'd probably just create a probe with a longer extension on here. But once it's done, then you can go ahead and take those paths, and then you can do a simulation. And if I run the simulation now, I'll just run through it quickly. You can see now that it's going to go through moving up, and now it'll move up as well again, where before it was going right through the part. Now it's actually going to rotate and go over to that part, and it's going to come close, but it is going to clear, and then it'll continue through the rest of the part. The last portion I need to do is I need to go ahead and post this. I'm going to post it to a DEMUS, standard DEMUS file, and the DEMUS file here is what I'm going to take. That's a DEMUS file, not meant to be read by human beings, but it puts everything in. And
for our viewers, can explain what DEMUS file is?
A DEMUS file, it would be equated to like a G-code file for a CNC machine. It's what actually runs the machine. And any machine, any CMM machine that's compliant with DEMUS 5.2 will allow this particular program to run on it. Okay.